Good afternoon. I'm Ron from Clover Park Technical College. Today we're going to be giving an online presentation because of the coronavirus. So if you can please bear with me, the presentation is going to be from 15 to 20 minutes long. And if you have any questions, you can please email me or Rajon, and let's get this started. So today's presentation is going to be on our capstone project and what is Megatronics about. So me and Rajon, we both are two students here at Clover Park Technical College. And right now we're in our capstone stage, which is meaning we're ready to graduate. That means we done completed all the necessary classes to be able to take the capstone. So our capstone project consists of a Brownville conversion. This project was handed to us last quarter in Applied Mech, where the project wasn't able to be completed. So me and my cohort, Rajon, we decided to ask the instructors if it was possible if we could complete the project as a capstone project, and it was granted. So we submitted all the necessary paperwork to do it. We set out and we gave them a presentation about what we're going to be doing, and it was granted. So the Brownville conversion of a Lincoln Series oven, basically a pizza oven. So the definition of a Brownsville conversion is basically we're taking legacy equipment and software that performs discrete functions, and we're going to turn it into basically. So what we're saying we're doing is the Brownsville conversion. We're going to take this old equipment and we're going to update it with software, and we're going to turn it into a reflow oven. That's what the conversion is turning it into a reflow oven. So a reflow oven is basically an oven that can produce these little things right here. These little things right here, they are called PBS or circuit boards, whichever one you want to call them. So the project at hand is to basically turn this oven into circuit boards. So the design functionality of the oven, what we're actually going to be making this oven to do. So the oven's going to be stacked. So that's the design we came up to stack the ovens, basically so we can mirror what's going on in one oven to the next. So we wouldn't have to go in and basically design two different ovens that could do two different things. Instead, we decided to design one oven, and we'll mirror it into the other oven. Exactly what we did to the first oven, we'll do to the second oven. So basically, what we needed to do is set some functionalities of what's going to go on in order to make these circuit boards. So we had to come up with the actual heat and temperature, what it takes to make the circuit board. So basically, it's a heating scale. It goes from 150 Celsius to the flux stage, which has at 183 Celsius, then to at the reflow stage that's at 220 degrees Celsius. Then it needs to cool. So I got another chart right here that's going to show you the cooling and all the zones that it would have to go through to complete it to make a circuit board. So in able to do this, we had to have certain things. So we needed some tools. So what we had for tools were wrenches, screwdrivers, sanders, various tools. Tom was able to let us go into the lab to get things we needed out of there. So the parts we ended up having that were available to us was the Lincoln Series electrical pizza oven 100, a Siemens 1200, a DC motor, AC motor, Dayton speed control, a PLC board, wires. So with that, we was able to come up with this, the essential functional chart of actually what was going to be going on when we press buttons on the PLC. So what was going to be going on was we'll press a button and the conveyor would come on, but it wouldn't move because the speed control would be on 0. But what would come on would be the PIDs. So the PIDs is going to control. So with the PID, we was able to come up with this wiring diagram for the PLC. So with the PIDs, what would happen is when he pressed this first button right here, and it'll go to there, come all the way around to here, come down to here. So once it got here, it would actually turn on the AC motor in the PIDs. So once those was on, the next move we could do would be to actually turn up the speed control. Once we turned up the speed control with the knob, we could vary the speed for the conveyor, which would in turn send the circuit boards completely through the oven, just with these simple button pushes. So that would be the programming for the PLC. So that all come into actually what we're doing right here. So basically, when we stop the conveyor, the PLC will read on the button that the oven light is ready to go. So basically, when the oven comes on, the light comes on, it's ready to go. The PID is ready to go. So we can start the oven. So how our oven is going to work is, when we press start, the first start button, the PIDs and the AC motor comes on. Once the PIDs send the signal to the PLC that it's ready, the temperature is, the first temperature zone is ready, then the speed controller would automatically come on and the conveyor belt would automatically start moving at the speed preset. So with this wire diagram, we're back at it with the PLC. So once we had everything on our mock system, because we created a mock system of actually what would happen when the program was running. Because one of the AC motors were hooked to a shaft inside the original pizza oven, we weren't able to simulate that in the class. So what we did was we got an AC motor with the same configurations as the motor hooked to the shaft, and we're able to do a mock. So this all represents our mock-up of what's actually going on in the PLC and the programming. So the mock is going to demonstrate basically what we couldn't do to the oven right now because of parts wasn't able to come in and because of the time restraints we're on. So we did a mock of actually what would happen. So I'm going to run you through the PLC programming. So this is the PLC button. So the refill oven works like this. So we press button 1, and if button 1 is normally open, right? So the button's always open. That was the code. So when the button is pressed, once the button is pressed, it would let the signal go through to L1. And we can go back to the other screen, and you can see that L1 is the start button. And the same thing with button 2. So basically we had 3 buttons that was on and off buttons. So when the first button came on, that was able to tell A1 to turn on the AC motor and the PIDs. Button 2, when that button was pressed, that button was to be able to tell the DC motor and the speed control to come on. And when button 3 was pressed, button 3 was to say, hey, this is for the AC motor by itself. So this one is going to represent the PIDs, and this one is representing the AC motor by itself. So even when this button comes on, this button is still on. It's waiting. Both of these buttons are how we wired it. Both of these buttons, one of these is going to its own circuit basically, but the neutral comes back around and hits this button right here. So when this button's on, this button's also on. So both of these buttons together are always on basically. So what we did was, because we ran out of time because of the school being canceled, so we did a mock-up of what would actually be happening to the oven. So we did ghost parts. So what we're going to do is we're going to go through and we're going to refab this. And this is going to be our on and off. And these are our buttons. And we're going to get rid of these buttons. And then this is where our PID and Dayton speed control and the PLC went right there. So what did we wanted to do? So the project overview, what was we trying to learn out of this and what was going on in the project? So what we were trying to learn out of this project, the project overview was we're trying to get to all avenues of mechatronics. We're trying to showcase all the skill sets that we have acquired in this class. We're trying to show our AC and DC skills. We're trying to show our motors and drive skills. We're trying to show our CAD skills. We're also trying to show our lean implication skills. And that was the overview of this. And basically, the problems that we occurred were wiring the e-stop and programming it. The configurations in order to wire an e-stop into a PLC program, they're pretty strict and they have a lot of guidelines that you have to set. And with the time restraints, I didn't have time. But for future projects, I will be able to knock that out of the box. And simulating the mock project. So simulating the mock project, I kind of saw it at the beginning of a waste of time. I wanted to go straight in and do the real programming of the stove. But over time, as weeks went by, I realized that we were waiting for parts and parts wasn't coming in. And I had already started looking at the PIDs, and I had pulled up the manual to basically go over the PIDs and all the different things we needed to do to make that happen. But then I realized if we just did a mock of exactly what were going to happen, that it would basically simulate the same thing, and then future students could take over from there. And that way they can use our manual and they can figure out exactly where to go from there. Because if you read our manual, you pretty much would be where we left off at. And how to be continued. Parts will be purchased to be available for integration by the next group of students. Retrofit all the new parts, so all those little ghost spots we showed, you can go in and put the parts where they need to go. Program the Siemens 1200 with the inputs and outputs from the SFC chart that we designed. Basically the inputs and outputs, we already have everything ready to go. All you'd have to do is go in and write a program for basically following our SFC chart and run tests and operations of the project. And this is going to complete our online presentation today. And if you have any questions, don't hesitate to email me. Thank you.